A bigger context window does not automatically beat retrieval. I'll show you when RAG wins, when long context wins, and how to choose without wasting tokens or quality. This is the setup you'll be able to run after this, which chooses the best approach and explains why with a latency estimate. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Think of a support workflow where you answer customer questions from a knowledge base of 3 documents. The question is simple. Do you shove everything into one big prompt and hope the model handles it? Or do you retrieve a couple of focused passages and let the model synthesize? People reach for long context when they want simplicity. They reach for retrieval augmented generation, or RAG, when tokens, freshness, or citations matter. At a high level, the decision is about trade-offs. Long context buys fewer round trips and simpler logic. RAG buys smaller prompts, explicit citations, and cheaper token cost per query. Success means accurate answers, reasonable latency, and affordable token use. We will build a tiny decision test. It compares total token size against your context window. It simulates a simple retriever that weighs relevance versus token cost. Then it scores freshness and citation needs and folds in latency. You will get a 1-line recommendation and a confidence gap before we finish. Now we check whether everything fits into one prompt. This snippet sizes a tiny corpus against a fixed context window to test if long context prompting is even possible. The list named docs holds 3 items with token counts, rough ages in days, and whether citations are required. The variable window represents the maximum tokens you can stuff into a single prompt. The expression need sums the token counts across all documents, treating a naive long context attempt as include everything. The Boolean fits compares total tokens to the window size to signal feasibility. If you increase window, fits may flip to true. If you add more documents, it can flip to false. The printed result quickly shows whether long context alone is viable. Next, we approximate retrieval with a tiny heuristic. This example approximates retrieval by ranking documents using a simple trade-off between match strength and token cost. The string Q is the query, and matches is a tiny interpretable proxy for relevance counts per document. The list ranks sorts docs by a score that rewards higher matches but subtracts a penalty for larger token sizes, biasing toward compact, relevant items. The slice top picks the top 2 documents as if a retriever returned them. The variable rtalk totals their tokens, and sav estimates the fraction saved versus dumping everything into a long context. Increasing the size penalty favors smaller docs and typically increases savings. The printed savings quantifies why retrieval can cut cost. Now we turn raw signals into a decision score. This code converts raw signals into a pragmatic decision score for long context versus RAG. The variable cov_lc measures how much of the corpus fits the window, capping at full coverage. The variables fresh_long and fresh_rag compute the fraction of fresh documents for each option using a 30-day cutoff. The Boolean cite_need flags when the retrieved set contains material that should be cited, which disadvantages long context. The weighted sums score_lc and score_rag blend coverage, freshness, and citation friendliness into comparable scores. Increasing the coverage weight favors long context. Increasing the citation weight favors RAG. The printed strategy and gap explain which path wins and by how much. Next, we fold latency and operational overhead back into the choice. This example adds latency and operational overhead to ground the choice in real SLA pressure. The variable rate models tokens per second. Overhead captures extra network or indexing time. Ops adds a small operational tax for retrieval components. The value LAT-LC estimates long context latency from total tokens, while LAT-RAG uses only retrieved tokens plus overheads. The variable faster labels the quicker option. Gain reports the time saved in milliseconds. The Boolean OK checks whether the faster path also meets a target SLA. Raising rates or lowering overhead tilts results toward RAG meeting stricter SLAs. The printed gain and SLA flag show the speed benefit in concrete terms. Now, we package this as a decision function you can reuse. This snippet wraps the framework into a tiny decision function that outputs long context, RAG, or hybrid. The function decide favors long context when everything fits, content is fresh enough, and citations are unnecessary. It picks RAG when the retrieved set fits, citations are needed, or retrieval freshness beats the whole corpus baseline. Otherwise, it returns hybrid, signaling a mixed strategy such as selective retrieval plus summarization. The variable mode captures the recommendation, while conf derives from the earlier score gap to reflect certainty. Tightening thresholds will push more cases into hybrid. The printed decision and confidence provide a compact, actionable baseline. In a real project, you would replace the toy relevance counts with a real retriever, and the token estimates with measured tokenization. The same decision flow maps to larger corpora. You keep the same signals. Only the thresholds and the latency model need tuning as you scale. Recap. It is a small decision framework comparing total tokens, retrieval savings, freshness, and citation needs. Use it when you must balance latency, cost, and provenance for question answering. One caveat: the thresholds are heuristic and need calibration on your real data and your real model. Next step: tune the size penalty or the coverage weight and rerun the decision across a larger sample of queries to measure how often the framework picks each mode. That single knob will show you how sensitive your pipeline is to document length. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.